Is everybody clear? Everybody's clear? Okay, so I'll let you know more on this later. All right, so the first thing I want to do is finish up section 10.1 by doing two more examples today. The first example that I want to do today is this example. So here I have the curve C given by x equals to 3 cosine t, y equals to 4 sine t. T is between 0 and pi over 0 to 2 pi. And the question is, what's the graph of this curve and what's the orientation of the curve? The idea here is that from the equation for x, I can divide both sides by 3, and I can obtain x divided by 3 is cosine t. And then from the second equation, I can divide the second equation by 4, and I get y divided by 4 is sine t, right? And then if I take the square of x over 3, and if I take the square of y over 4, I'm going to get cosine squared plus sine squared. And once again, we know then that x squared over 9 plus y squared over 16 is going to be 1. Is that derivation clear, how you are obtaining that equation involving x and y? So we eliminated the parameter t, obtained an equation involving x and y. And if you look at that equation, this should be a familiar equation, right? This is like the graph of that equation is like the path of a planet, which is like a deformed circle, right? What is it called? Ellipse, yeah, ellipse. And the equation of the ellipse is given by that. Now, based on this, I can decide how the ellipse is expanded over the x-axis. You have 9 below x squared. So 9, what's the root of 9? The root of 9 is plus or minus 3. So you know that the ellipse is going to extend from negative 3 to positive 3 along the x-axis. And the number below y squared is 16, and the root of that is plus or minus 4. So the ellipse is extended over the y-axis from negative 4 to positive 4. Does that make sense? Everybody's clear? So I get the ellipse like that. Once I know that the graph of the equation is an ellipse, now I still have to figure out what's the graph of the curve. Is the graph of the curve entire ellipse, or is it only part of the ellipse? The second question is, what's the orientation? So how am I going to figure that out? In order to figure that out, I'm going to look at the behavior of the x-coordinate of the curve. So what's the x-coordinate? The x-coordinate of the curve is given by 3 cosine t. So let's figure out the behavior of 3 cosine t. When t is 0, when t is 0, what's the value of x? When t is 0, the value of x would be 3 cosine 0, and 3 cosine 0 is what? 3, right? Because cosine 0 is 1. So I know when t is 0, x is 3. Okay, when t is pi over 2, what is x? When t is pi over 2, x would be 3 cosine pi over 2. So what is 3 cosine pi over 2? Well, cosine pi over 2 is 0, so I get 0. Now, same way, what is the x value at pi? The x value at pi would be 3 cosine pi. Cosine pi is negative 1, so you get negative 3. What's the x value at 3 pi over 2? The x value at 3 pi over 2 would be 3 cosine 3 pi over 2. Cosine 3 pi over 2 is 0. So So once again you get 0. And lastly, at 2 pi, cosine is again 1, so x would be 3. So what's the behavior of the function x? From 0 to pi over 2, the function x is decreasing. And from pi over 2 to pi, it is still decreasing to -3. From pi to 3 pi over 2, it is increasing from -3 to 0. And from 3 pi over 2 to 2 pi, the function is still increasing from 0 to 3, right? So that's the behavior of x. Okay? Once I know that, I actually got the orientation, and I also know whether I obtain the entire ellipse or part of the ellipse. Why? Well, let's think about what point on the curve do I get when t is 0? When t is 0, what is x? When t is 0, x is 3, y is 0. So if you agree with that, then I get this point 3, 0. Right? Once I get this point, now think about what is happening. As t goes from 0 to pi over 2, where are you at pi over 2? Where are you on the ellipse at pi over 2? At pi over 2, the x value is what? 0. X value is 0. Y value is 4, right? So at pi over 2, you are at the point 0.04. So what is happening between 0 and pi over 2? Between 0 and pi over 2, the x value starts at 3 and decreases to 0, right? So if the x value is going from 3 to 0, that means you're moving what direction? You're moving counterclockwise, right? And you're going to that point at 0.4. Am I right? Now what is happening between pi over 2 and pi? Between pi over 2 and pi, x is decreasing from 0 to what? X is going from 0 to -3, right? So what does it tell you what's happening? You're now moving from the point 0.4 to the point -3.0, right? So you're right here. Between pi over 2 and pi, that's what's happening. Now what is happening between pi and 3 pi over 2? Between pi and 3 pi over 2, now x value increases from -3 to 0. So x value at pi is -3, and then it increases from -3 to 0, and then you're going from this -3.0 to the point 0, -4. Okay? So you get the point 0, -4 at what time? T equals to 3 pi over 2. Remember here you are when t is pi. And then finally you come back to the initial point at the time 2 pi, right? Am I making sense? So how many times did you trace the ellipse? Exactly once, right? Exactly once. And you got the entire ellipse. Now, let me change the question a little bit. Let's say I change t in the formulas for x and y. So replace t in the formulas for x and y by 2t. How does it change the problem? You go around twice. Now, change it a little bit more. Let's say instead of t, I have half of t. You get which half of the ellipse? The top half of the ellipse, right? Everybody understands those variations? Those variations are okay? All right. Any questions at all? Okay, I promise this will be the last example of this section 10.1. This time I have the curve C. Now x is hyperbolic cosine t, y is hyperbolic sine t, and t varies over the entire real line. Once again, the same question: what is the graph of the curve? And if you know the graph, what's the orientation of the curve? Is everybody okay? Everybody's okay? Let me delete something here. I guess you have seen this already, but doesn't matter. Okay, first of all, the trick is similar. In order to get an equation involving x and y by eliminating t, the idea is that square both of the equations for x and y. So what's the square of x? Square of x would be hyperbolic. Square of the hyperbolic cosine. Square of y would be the square of the hyperbolic sine. So I get x squared is a hyperbolic cosine squared t. Y squared is hyperbolic sine squared of t. Do we know an identity involving hyperbolic cosine squared and hyperbolic sine squared? Yeah, if I look at x squared minus y squared, I'm going to get hyperbolic cosine squared t minus the hyperbolic sine squared of t, and we know that it is 1, right? So the equation that I am getting is x squared minus y squared equals to 1. And all of you should have seen this equation in high school, right? What's the graph of x squared minus y squared equals to 1? It's not a circle. It's not an ellipse, right? So what is it? It's the hyperbola, right? Now, the hyperbola has two parts. Here you have a negative one here and a positive one here. So it looks like two parabolas, right, together. One opening to the right from vertex at 1, the other one opening toward left, vertex at negative 1, right? So the hyperbola is given by two parts. Now, is the graph of C all of it? Am I making sense? What's the graph of C? Is the graph of C the entire hyperbola, or is it only half of it? Right? What part of the hyperbola belongs to the curve C? We have to determine that. So how would I determine that? How would I determine that? I don't know why I have a vertical line there for no reason. Okay, what's the hyperbola? What's the graph of C? Do I know that? Do I know that? Well, what is C? C is x is hyperbolic cosine, y is hyperbolic sine, right? Anyone remembers the graph of hyperbolic cosine and hyperbolic sine? Let me tell you what that is. The hyperbolic cosine is this red curve. Okay, this height here is 1. Okay, that's the hyperbolic cosine. So that's the graph of x as a function of t, right? This is the graph of x of t as a function of t. Y of t, that's hyperbolic sine t. So this is hyperbolic cosine t, and y would be hyperbolic sine t, and that's the graph of hyperbolic sine t. So hyperbolic sine t goes from negative infinity to positive infinity. However, hyperbolic cosine t, what's the range? The range of hyperbolic cosine is from 1 to infinity, right? What does it tell you about x? X is bigger than 1, right? X is at least 1. So then, what does it tell me about the curve C? Can the curve C be the left half of the hyperbola? The left half of the hyperbola, what is x? X is less than negative 1, right? However, x is hyperbolic cosine, so x has to be bigger than 1, right? So that tells you, because x is hyperbolic cosine t, and we know that hyperbolic cosine t is at least 1, we know that the left part of the hyperbola is not going to belong to C. So we only get the right half. Now the question is, do I get the entire right half? And if I do, what's the orientation, right? Is everybody clear? You guys are with me so far? I get only the right half of the hyperbola because x has to be at least 1. Right? Because hyperbolic cosine t is at least 1, no matter what t is. Now, what's the let's try to figure out the orientation, and in the process, we're going to also see that we are going to get the entire right half of the hyperbola. How? Once again, what is x? X is hyperbolic cosine t, y is hyperbolic sine t, right? And I know the graphs of them. Now, let's think about this for a second. What is happening as t goes from negative infinity to 0? As t goes from negative infinity to 0, what is happening to x? As t goes from negative infinity to 0, what is happening to x? Look at the graph of x. X as a function of t, the red curve, right? As t goes from negative infinity to 0, as t goes from negative infinity to 0, what is happening to x? It comes from infinity, decreases to 1, right? X goes from infinity, decreases from negative infinity to 1, right? You agree? What is happening to y? Y increases from negative infinity to 0, right? Y increases from negative infinity to 0. Y increases from negative infinity to 0. X decreases from infinity to 1. You agree? So what does it tell me about the curve? Well, as t goes from negative infinity to 0, I know that x is decreasing from infinity to 1, right? X is decreasing from infinity to 1. What is happening to y? Y is increasing from negative infinity to 0, right? So what does it tell you? That I must be moving upward direction along the curve starting from negative infinity. Y at negative infinity, x at positive infinity, right? Y at negative infinity, x at positive infinity. I'm going to start there, and then I'm going upward until I get to the point 1, 0, right? That's what it means, right? Is everybody okay? X is decreasing from infinity to 1. Y is increasing from negative infinity to 0. So put them together, it says that the curve starts at x at positive infinity, y at negative infinity, and then you move upward until you get to the point 1, 0. And then what's happening? Once again, if you go back to the graph of x and y, after 0, what is as t goes from 0 to infinity, as t goes from 0 to infinity, now x is going back up again, right? X is going from 1 to infinity, y is going from 0 to infinity. So right at this point, y is 0, x is 1. Y is 0, x is 1. So now we know that x is increasing from 1 to infinity, y is increasing from 0 to infinity. Y increasing from 0 to infinity, x increasing from 1 to infinity. So put them together. X is going to infinity, y is going to infinity. So put them together, you know that you're moving in that upward direction, right, along the curve. And if you think for a second, you see that you're getting the entire right half of the hyperbola in this way. Does that make sense? You guys ever figure that? Any questions? No? Okay, so that was the last example that I wanted to do. And if you don't need time to write that down, let's move on to this new section, 10.2. Okay. The problem that I want to address today is, suppose that I have a curve, and the curve is given by, the x coordinate of the curve is given by x of t. The y coordinate of the curve is given by y sub t. And let's say t lies in some interval from a to b. It doesn't have to be in a finite interval, but just for the heck of it, I'm assuming that t varies over a finite interval, but it doesn't have to be. A and b could be plus or minus infinity. Okay, you can have an infinite interval for t. Now, the question that I'm trying to ask here is, let's pick a point on the curve. Let's call that point x0, y0. So I'm fixing a point x0, y0 on the curve. And let's say we obtain the point x0, y0 at the time t0. Now let's for a moment think about this curve as the path of a moving object. So we are saying at time t0, the object goes over the point x0, y0. Okay, the position of the let's say a bug moving along the curve, the position of the bug at time t0 is x0, y0. So what is x at time t0? X at time t0, this is what we are calling x0. And y at time t0 is, we are saying, is y0, right? Let's say capital T denotes the tangent line at that point. Tangent line at the point. Why do I care about the tangent line? Yeah, it gives you it's not the velocity, it gives you the direction of the velocity. The velocity would be a vector with two components, right? But the slope is telling you the direction of movement at that point. Okay, and it is an important quantity, and so we want to know what is the slope. So we want to know, let's say the slope is given by m. We want to know the slope at that point. Another quantity that I also want is, I want to know the concavity at the point x0, y0. Okay, is it concave up at that point? Is it concave down at that point? Now, how can I come up with the slope? How can I come up with the slope? I am going to make some assumption here. I'm going to say that let's suppose that I can find a very small portion around this point. So I'm picking a small portion of the curve around the fixed point. Okay, and let's say you obtain that portion when t is between some number alpha and beta. So when t is between alpha and beta, let's say I obtain that small portion around the point x0, y0. Is my notation clear? So I am picking a portion around the point x0, y0, very tiny portion, and I'm going to say that portion defines y as a function of x. Am I making sense? The portion that I picked around x0, y0, I'm going to assume that portion defines the y coordinate as a function of the x coordinate. How would I say that? Well, it satisfies the vertical line test, for example. Okay? So I'm assuming around the point x0, y0, there is a small portion of the curve where I can think of y as a function of x. If I can do that, then what would be the slope? Can you tell me what the slope would be if I can assume that y is a function of x around the point x0, y0? Well, if that portion that I fixed, if it is the graph of a function y of x, then what would be the slope? The slope would be given by the derivative of y, right? The slope would be the derivative of y with respect to x evaluated at x0, right? Am I right? Given that I have a portion around x0, y0, that does represent y as a function of x, right? So I am assuming here what? I am assuming that a small portion, say for t between alpha and beta, whatever portion I get, where of course I'm assuming t naught where? T naught is in this interval, right? So there is a small portion around that point x naught, y naught that represents y as a function of x. If that's the case, then the slope will be given by the derivative of y with respect to x evaluated at x naught. Okay, that's all I'm saying here. Does that seem reasonable to you? Now, what would be the how can I come up with the concavity? What quantity will tell me the concavity of the curve? Yeah, you look at the second derivative of y with respect to x, evaluated at x naught, and it's going to tell you what's the concavity, right? Plus, second derivative is plus would mean what? Concave up. Second derivative is negative would tell you concave down, right? You agree? But the question is, how do I come up with then dy dx at x naught, right? How do I come up with dy dx? Because probably I am not going to be given an explicit formula for y in terms of x. Most probably you wouldn't be able to find y as an explicit formula in x. Right? If I have an explicit formula for y in terms of x, then I can just do the problem as usual that I did in Calc 1, right? So how do I come up with dy dx at x naught? That's the question that we want to answer. Okay, just let me know whenever you're done writing down this paragraph here. Okay, so how do I come up with dy dx at x naught? The idea is the following. Where were I? Okay, this is where I was. Yeah. Now, the idea is that remember, you're given y as a function of t in the problem, right? Y is y sub t. So you have a formula for y in terms of t. Now, note that we are thinking of y as a function of x, right? We are thinking of y as a function of x. We don't know the formula for y in terms of x, but for a second, imagine that there is a formula for y of x, right? If I have a formula for y of x, note that there is a formula for x in terms of t that's given in the problem. So I can evaluate y of x of t, right? Because I have a formula for x in terms of t. So notice that y of x of t must be the same as y of t, right? Eventually, if you look at y of x, say you have a formula for y of x, replace x by x of t, the formula for in terms of t, you're going to be able to write y in terms of t, right? So if you write y in terms of t via x, that should be the same as y of t given, right? You agree? Imagine you have a formula for y in terms of x. Whatever the formula for y in terms of x is, replace x by x of t. That's going to give you a formula for y in terms of t. But you already have a formula for y in terms of t in the problem. So that means y of t and y of x of t are the same. We can use this equation, and now I can say what is y prime of t. Notice that I don't know y of x, right? I don't know y of x, but I'm trying to use that to come up with a formula for dy dx. So what is y prime of t? Y prime of t would be whatever the derivative of y with respect to x, with respect to t is from the right hand side. But if you take the derivative of y with respect to t on the right hand side, you have to apply the chain rule. So what do you get? You get y prime of x of t multiplied by x prime of t, right? Is everybody okay? Is it making sense? Now, it's a matter of rewriting stuff. So y prime of t, let's evaluate both sides now at t naught. So I get y prime of t naught, and then I get this is y prime of x of t naught, x prime of t naught. Notice that what is x of t naught? Remember x of t naught was x0, right? We fixed the point x0, y0, and we said x0, y0 occurs at t naught, right? So I know that x of t naught is x0, so I'm going to replace that like this. And finally, I'm going to change the notation here. Instead of saying y prime of t naught, I'm going to say, what is this? This is the derivative of y with respect to t, right? So I'm going to call that dy dt evaluated at t naught. Y prime of x naught. Well, y prime of x naught, that's just dy dx evaluated at x naught. Right? And then finally x prime of t naught, that's just dx dt at t naught. Is that making sense? Eventually, notice that I can solve for dy dx. I can solve for dy dx, and I get a formula. I get a formula for dy dx at x naught, which basically says dy dt at t naught divided by dx dt at t naught, which is nice. Notice that I did not know a formula for y in terms of x. However, I was able to come up with the derivative of y with respect to x at x naught by using given information. I am given y with respect to t as a function, right? As an explicit function. I am given x as a function of t explicitly. So I can explicitly compute dy dt, I can explicitly compute dx dt and evaluate them at t naught. And that's going to give me the derivative of the function y with respect to x at x naught. Is everybody okay? What's the relationship between t naught and x naught? Well, x naught is the value of x. X naught is the value of x at time t naught. Right? This is what you have to remember. The dy dx is dy dt divided by dx dt. That's the formula that you need. That's the slope. That's the slope formula for a curve. Did the derivation make sense? Okay, I think everybody can use the formula. Once you have the formula in front of you, you can just plug in stuff, come up with the slopes and so on. But if you understand, you should at least try to understand the derivations like this, because that's what's going to help you increase your reasoning skills. Okay. Now, I have the slope formula here. Now, remember the concavity? The concavity would be given by the second derivative of y with respect to x evaluated at x naught. What would be the second derivative at x naught? The second derivative at x naught will be, of course, the derivative of the derivative evaluated at x naught, right? So you take the derivative of the derivative dy dx at x naught at the end. I'm going to rewrite d dx of dy dx. Rewrite that as dy prime, ddx of y prime, ddx of y prime at x naught. Now, I'm thinking of y prime. This could be confusing. Am I thinking of y prime as y prime of t, or am I thinking of y prime as y prime of x? So that's why I'm specifying I am thinking of y prime as y prime of x. Otherwise, it's confusing. Right? dy dx can be written as y prime of x. So I am thinking of y prime as a function of x here. Now, if I had dy dx, do I know the formula? If I have dy dx, what's the formula? If I have dy dx, then the formula is what? dy dt divided by dx dt, right? A few minutes ago, I found the formula for dy dx, right? dy dx was dy dt divided by dx dt. Now y prime is just another function of x, right? Just like y is a function of x, y prime is just another function of x. So the formula for dy prime dx would be very similar to the formula for dy dx. What will that be? Well, it will be the derivative of y prime with respect to t divided by dx dt. Am I making sense? If I have dy dx, I will be getting dy dt over dx dt. If I have y prime, I'm going to get dy prime dt over dx dt. Both of them would be evaluated at t0. Am I making sense? Is that making sense? So the second derivative then is going to be, you take the derivative of dy dx with respect to t divided by dx dt. Both of them are evaluated at t0. So finally, the second derivative formula that I get is that this is the d dt of dy dx evaluated at t0 divided by dx dt at t0. Okay, and that second derivative will tell us what's the concavity at x0. Is everybody okay? Any questions at all? Any questions at all? You guys are okay with that? All right. There are a couple of things that we should be aware of here, okay? One is curves are more complicated than the graph of a real valued function of one variable. That is, if I have y equals to x squared, those graphs are much simpler. But if I have the graph of a curve, the idea of tangent could be more complicated. So in the first case, I might, given a point P on a curve, there might be exactly one tangent. However, there might be a point P where you have two distinct tangents. Why? Think of a bug moving along the second graph here, moving along the second curve. It's like a loop, right? It's making a loop at the point P. So think of, even though I get the point P there, notice that the point P is traced at two distinct times, T1 and T2. So the object goes through the point P at some time T1, and then it comes back to the same point at another time. So think about it in terms of the velocity. The velocity at the point P at time T1, there is a velocity at time T1 at P. But when it comes back to P again, there is another velocity at the same point P, but at a distinct time, at a different time, right? So it does make sense that at the point P you have two distinct tangents. The tangents tell you the direction of movement at the point P at the times T1 and T2. Am I making sense? So at time T1, the tangent line is the pink one, and at time T2, the tangent line is the red one. Is this making sense why you might have two tangents? Because the velocity at P at two distinct times will be different. Could be different. Is that okay? However, you also might have a situation where you have a point P where the curve makes a sharp corner. In that case, you will have no tangents. The tangent line does not exist at the point P. Am I making sense? You can see why it shouldn't, because what is happening on the left-hand side of P? If you look at the left half of the curve at P, so look at the left side of P, what is the slope at any point there? The slope at any point would be positive, right? The slope at any point on the left of P would be positive, right? So notice that as you get closer and closer to P, you're getting some positive slope, right? Look at the points very, very close to P. At those points, the slope is positive. But as soon as you go on the other side of P, the slope is becoming what? Negative. So you have a jump, right? If you look at the graph of the slopes, the function will be on the left of P, you'll get positive slopes, right? The graph will be on the upper side of the x-axis. All of a sudden, as soon as you reach P, after that, so what I'm saying is that if you look at the graph of just the slope, M, let's say where you get the point P at some time t0, okay? So until you get to that point, the slopes are positive. But all of a sudden, something happens at t0. At t0, all of a sudden after t0, the slope becomes negative, right? So if you look at the graph of the slopes, there is a jump at t0. Is that making sense? Before t0, the slopes are positive. After t0, the slopes are negative. So it tells you that if you think of this curve as the position of a moving bug, something happens at P. It could be something bad that happens to the bug. Am I making sense? Maybe someone is someone is slapping the bug maybe or something. It changes the direction of the path. Am I making sense? Or maybe it's the moving car or something, and a big truck is bumping into it and changes the direction of the movement of the car.
Yeah, but which one is very close to
Right. So you get. My point is, something happens at P that changes the motion. That changes the motion. Okay, and that's why you don't have a tangent line at P. Okay. All right. So I am going to begin from there.